Here we are, starting a new chapter in our lives. Isn't that a beautiful thing? I'm so excited, you guys. I hope you're excited too. Well, this section, you know what, if you look at the title, at first, especially if you're just kind of half asleep or you're, I don't know, not too excited to be here, it says radical expressions and functions. At first you say, wait a second, I thought this was a new chapter. Isn't that what we just talked about? Well, it's kind of weird. Okay, the last chapter we talked about, actually it's almost the same word but not quite. It's rational with a T expressions. So those guys are ones, where you have a fraction with a polynomial like, I don't know, x minus 1 over x squared plus 4x plus 3 or something like that. That's a rational expression. Radical expressions with a D is anything with a root. So remember, I don't know, you've probably seen square roots before, like what's the square root of 5, or what's the square root of 24 or 25. That's what a radical is. So they almost sound like the same word, rational, radical, and they're right, back to back. We learn them as topics back to back. But there's two different topics. Radical is roots and rational are fractions with polynomials. So I think you'll like this section. If you've seen roots before, you're going to have a good time. Alright, so let's see. The next thing is just the definition. We've already kind of talked about this. A radical expression is an expression containing a root. It could have a square root or a cube root or a fourth root. We'll see those guys soon. But yeah, just keep that in mind. You see radical, that means some kind of root is involved. Okay. The first thing is we'll look at square roots specifically. We'll see the other kind of roots later. But a square root, okay, they say the number c is a square root if c squared equals a. So that's very confusing, but really the way you can think of that is, if you're looking for, if they say what's the square root, you can ask yourself, what can be squared, raised to the second power, to give this number. And I mean this, they'll give you a number. They're going to say, oh, what's the square root of blah, blah, blah? Just look at that number and say, what can I square and get that number? That's all. So okay, let's see. This first thing they mention here is, they say, for example, 16 actually has two square roots, -4 and 4. And that's because, notice if you square -4, you get positive 16, and that's why it's a square root. So, I mean, yeah, pretty much you're saying, well, what's 16 square root? Well, -4 is one of them, because if you square that guy, you get 16. But not only that, what if you square positive 4? You also get 16. So really, every number has two square roots. It's like, if you can think of one of them, just make it negative, and that's another one, really. 4 and -4. So let's try this next one. They say, what are the square roots of 100? So I'm asking myself, what can I square and get 100? Well, I think 10, right? Because 10 to the second power is 100. But not only that guy, but his negative is also a square root. Because if you square -10, you also get positive 100. Let's try one more, and then we'll kind of get more specific. How about 49? Okay. What can you square or raise to the second power and get 49? 7, right? 7 times itself, or 7 squared is 49. But not only him, but his negative as well. -7 squared is positive 49 also. Alright, so that's the idea, that every number has two square roots. But now, as soon as we get used to that idea, we say, okay, that sounds good. Now we go on to this new definition that we're going to be using from now on. The principal square root of a non-negative number. So we don't talk about roots of negative numbers. It doesn't make sense. And we'll see why pretty soon. So the principal square root of a non-negative number, it has to be positive. It is its non-negative square root. So basically what they're saying is, from now on, whenever you see this symbol, which is what we're used to, a square root, that means we only want the positive square root. So that's what we'll be doing from now on. Although we know there are two answers, there are actually two square roots to every number. When you see that symbol, we're just going to say, alright, look, we know there are two square roots, just give me the positive one, that's all I want. And that's why probably the negative one didn't come to you right away, because if you've learned square roots before, you probably learned the principal square root, and you only talk about one of them, the positive one. So from now on, we're just going to talk about the positive one. And that's why you notice in these above examples that we did, they said it in words, right? They said, like, what are the square roots of 100? Instead of writing the symbol, the square root symbol, they just said it in words, which means it's possible to have two answers, the positive and the negative. But notice in this example below, example 1, they have all the symbols, the square root symbol, which means we only want the positive answer. It's kind of tricky, but yeah, just keep in mind principal square root is what they want here, which I know because they wrote the symbol, the square root. Only the positive root. Alright, so part A, you're saying, what's the principal square root of 81? So you just have to ask yourself the same thing. What can you square and get 81? That'd be 9, right? Because 9 to the second power is 81. And I would say also negative 9, but I know that they want just the positive answer. So I'm done. That's it. Now let's try the next one. Now it's, what's the square root of 1? In other words, what can you square and get 1? Actually 1, right? I know 1 times itself is 1. So that, if you wanted to, you could say, like this guy, he's because 9 squared is 81. And this guy's because 1 squared is 1. If I square this guy, I get this guy. But 1's kind of a weird one. He's his own square root, which is pretty rare. You don't see that too often. How about 25? What can you square and get 25? I know that guy. That's 5. So pretty much, I mean, as long as you know your times tables, you kind of know what the squares are, you know. What times itself is this number, you know? Is it 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. And this guy's because 5 squared is 25. How about the next one? Now they've got, okay, the square root of 64, and they've got a negative in the front, which is kind of weird. But you know what we can do? Since the negative's in the front, we can kind of ignore the negative. I'm just going to say, I know this is going to be negative something. Now I just look at the square root. 64 square root. What can you square and get 64? Or in other words, what to the second power is 64? That's 8. So the answer is negative 8. So if you see a negative in front of a square root, you know, just kind of carry it along. It doesn't really matter. It's just, what's the negative root of 64? Well, it's negative, whatever the root of 64 is, 8. So that's because, what is it? 8 squared is 64. Yeah. There we go. Yeah, so if you see a negative in front of a root, just ignore it. Don't worry. It's just carried along in your answer. However, on the other hand, what if you see a negative inside a square root? That guy's actually imaginary. So you shouldn't see a negative inside a square root, and that's kind of part of the definition here. Up here when they said what the principal square root is, you know, they say, what's the principal square root? It's you want to take it of a non-negative number. But they're trying to take a square root of a negative number here. It's imaginary. That's because, why would that be? Because what they're asking for is like, what, let's say x, I don't know. What can you square and get this number, negative 64? Actually, that's impossible, right? How can you square something and get a negative? It's impossible. Whenever you square something, it becomes positive, you know? You square a positive, it's positive. Square a negative, it's also positive. This is an impossible question. What can you square and get a negative, you know? It doesn't make sense. So that's why we say it's imaginary. It's not even a real number. It's an impossible question, so there's an impossible answer, imaginary. So if you ever see that, you know, in your homework or whatever, you see the square root of a negative, just write the word imaginary. Alright, the last one here, let's look at part F. Now it's asking the square root of 4 over 121. Well, you know what, we'll learn pretty soon that these guys, if it's a fraction, you can think of it as the square root of the numerator and then the square root of the denominator separately. So you don't have to worry about actually thinking of the square root of the entire fraction. Just kind of split up the root, give the numerator its own root, think about that. Give the denominator his own root and think about that. So in the numerator, I'm looking at the square root of 4. I know that's 2 because the square root of 4 is asking what can you square and get 4? Well, that'd be 2 since 2 squared is 4. The denominator, the square root of 121, that's asking what can you square and get 121? I don't know, that guy's 11 because 11 times 11 is 121. So there it is. You can, yeah, if you ever see a fraction inside of a root, just think of the numerator and denominator as root separately. There's no need to keep it complicated by leaving it as 4 over 121, the whole thing square root. Don't even worry about that. And on that one, if you want to write y, you could say, you know, if you're trying to prove it to yourself or prove it to someone else, it's because the fraction we just got squared is the number inside the root. Because if you square the 2, you get 4. If you square the 11, you get 121. So that is true. We got the right square root. Okay. Sounds good, you guys. So now, just for fun, let's combine this with the idea. If you remember, we started a little bit of functions. We talked about functions a little bit. So this one's giving us a new function. We haven't seen a function with a square root yet, and there's a good reason for that, because they figured we weren't ready yet. But now that we've kind of talked about square roots, now we're ready. The function f of x equals the square root of 2x minus 20. Okay, we want to find these values. Let me see, I'm going to write those guys out. We want f of 4 first. That's going to be something. And then we want f of 10. That'll be something. And then f of 12. And then the last guy, f of 28. That's a big number. Oops, sorry. Alright, I'm going to find all those guys. Alright, I'm going to kind of section them off so I don't get confused. But if you remember from the function section, we said, if you want to find, for example, the first guy, f of 4, all you do is take the function and replace x with 4. And that's it, yeah, so I'll take the x in that function and replace it with 4. So I'm going to rewrite that function. He looks like the square root of 2 times x, but I want to replace x, and then minus 20. Actually, that's how these are all going to look. The square root of 2 times something minus 20, the square root of 2 times something minus 20, and then same thing with this guy, the square root of 2 times something minus 20. It's just that the something's changing. In the first one, it's a 4. So I'm asking, what is this thing when x is 4? So I'll replace that guy. The second one, I want to know what happens when x is 10. So 10 will go in for x. The third one, I want a 12 where x goes, so he'll go there. And the last one, you want x to be 28, so I'll put a 28 where x was. And then it's just a matter of simplifying from there. The left one, we got the square root of 2 times 4 is 8, minus 20. Okay, what's 8 minus 20? Negative 12. Uh-oh. You said if you have a square root of a negative, that's imaginary. So this answer doesn't really exist. Square root of a negative. It's if you have a negative inside. Because remember, in example 1 part, what was it? Part D. Sorry, part D, we had a negative outside the root, and that was fine. The answer was a negative 8. But as soon as it's inside, that's when you have to be careful. That's imaginary. So just because there's a negative, it doesn't mean it's necessarily imaginary. It's only when the negative's inside the root, not outside. Anyway, that's kind of beside the point. Let's try this guy. 2 times 10 is 20, and then we're minusing 20. So it's 20 minus 20 is 0. Okay, that's kind of interesting. What's the square root of 0? Well, what can you multiply by itself, or what can you square and get 0? 0, right? Yeah, 0 squared is 0, since 0 times 0 is 0. It's kind of interesting. Alright, what about the next guy? It's the square root of 2 times 12 is 24, minus 20. 24 minus 20 is 4. So it's the square root of 4, and we saw that, I think, above, didn't we? It was 2. Since you're asking, okay, what's the square root of 4? That means, what can you square and get 4? The answer would be 2. Alright, so far so good. We got one more here, and then we can move on. So it's the square root of 2 times 28. Okay, what's that? 56, I think. Minus 20. Okay, then the square root, okay, 56 minus 20, I believe, is 36. Well, that's a good one. What can you square and get 36? 6, right? Yeah, because 6 times 6 is 36. Perfect. Alright. Interesting. So it's good to know that functions can be, or you can use this stuff with functions too. So a lot of, actually a lot of the things we encounter, the rational expressions, these radical guys with roots, everything we encounter can be thought of as a function. So functions are very broad things. We can kind of involve them in all types of things that we're talking about here. Okay, the next concept, there's kind of a lot going on in this section. I'm sorry about that. What does it say here? It says, for any real number a, and by real number they just mean it's not imaginary. So you don't want any weird imaginary stuff going on like we saw before where you have a negative inside a root. I don't want to see that, but as long as it's a real number, it's not imaginary like those guys. It's kind of weird looking, but it says the square root of a squared is the absolute value of a. I don't know if you remember the absolute value. Remember absolute value just pretty much makes everything positive. So if you have a negative inside absolute value, it becomes positive. If you had a positive, it stays positive. So keep that in mind. Yeah, absolute value just means make this number positive. But really a more practical way to think of that is a square root and a square cancel each other. So notice that's kind of what's going on here on the left side. You have a square root and a square. So really they're opposites because remember a square root asked, what did you square to get this? So it kind of goes backwards from a square. That's why they're opposites really. They undo each other. It's kind of like if you take a number and you multiply by 3 and then you divide by 3. You just kind of undid your work, right? You multiply by 3 and then you divide by 3. Why'd you do that? Those are opposite operations. It's the same thing here. A square root and a square are opposite operations. So you can think of them as they kind of cancel each other. Notice the square root and the square disappear, but they leave an absolute value in their place. And it's all because you have to have that absolute value because we don't want to see a negative inside a square root. So that's kind of why the absolute value is there. It's saying, okay, yeah, the square root and the square cancel, but don't you dare make that number negative because it can't be negative. Because square roots don't take negatives into them. Alright, let's see. Just to play around with that concept, let's look at part A of example 3. So we got 49, what is it? 49y squared inside a square root. Okay, that's kind of tricky because this is the first time we've seen a number and a variable inside a square root. But you know what you can do? We'll see this later, but there is a property. Actually, if you've used this one before, remember above, we already used this one, but if you have a fraction inside a root, you can split it up into a root of the top and the root of the bottom. But you can also do that with multiplication. If you have two things multiplied inside, a times b, you can say that's the square root of a, square root of b. Those are pretty useful. Just keep in mind, though, that's only for if you're dividing them, like here, or if you're multiplying them, like here. If you're adding or subtracting inside a root, you cannot split up the root. And we'll go over those properties more later. Those are pretty important. But notice in part A, I have two things multiplying inside. I have 49 multiplying by y squared, so I'm able to simplify this or split it into two roots, which makes it easier because then you kind of focus on one, simplify it, and then focus on the other. So first, the square root of 49, that's 7. And that you don't need an absolute value for because it's just a number. But the variable guy, that's what we got to worry about. So I can think of it as the square root and the square cancel like this property shows. I always actually cancel them out, so I kind of remember. But it says they cancel, but you have to leave an absolute value where they were before. I know it looks like a weird answer, but that's it. It's 7 absolute value of y. And I know absolute value, usually you can simplify that. Like if y was a number, or if I knew what y was, I'd be able to simplify that and write that as just some number. But because I don't know what y is, I don't know whether I should, if y was positive, I'd leave it alone to take its absolute value. But if y was negative, I'd change its sign to make it the absolute value. So because I don't know what y is, I can't really say what to do with it to make sure it's positive, and that's why I can't remove the absolute values. Can't remove absolute values from a variable since we don't know what that variable is. Or basically we don't know if that variable is positive or negative. No. If it's a positive number or a negative number. So if we knew if it was one or the other, we'd be able to simplify it, but we have no idea whether y is positive or negative. And that's why we just have to leave it like that, unfortunately. Let's try part B here. And notice part B looks complicated. It's t minus 4 in parentheses squared. But still, you're kind of thinking of it as, that kind of looks like the square root of a squared, the thing that's in the property there. So really, I can think of that as the square root and the square cancel, but I have to leave what was inside inside the root in absolute values, t minus 4. And unfortunately, that's another one where I don't know what to do with that, so that's it. And again, that's because I don't know what t is. If t is positive or negative, then t minus 4 could be positive or negative. If it was positive, I'd leave it alone, because that's what the absolute value says to do. But if t minus 4 is negative, then I have to change the sign to make it positive. So I don't really know what to do with this because I don't know what sign t has. And so that's really as good as it gets. Unfortunately, I can't do anything with that. And the absolute value will not change the sign in the middle. It's not like, you can't say t minus 4 absolute value is t plus 4. That's not true. And that's because, again, it's confusing, but t could be anything. Like what if t is negative 5 or something? What if you put negative 5 there? Negative 5 plus, or minus 4, sorry. That's negative 5 minus 4 is negative 9. Absolute value of negative 9 is positive 9. But if you put a negative 5 here, negative 5 plus 4 is negative 1. Those are different things. So really you can't do that. It's not like The absolute value just changes the sign between t and 4. No, it's too complicated for that. Since we don't know what t is, we have no idea if t minus 4 is positive or negative. Yeah, even if you change that minus to a plus, it still could be that t plus 4 is negative. It depends what happens with t. So when variables are involved, don't even try to take absolute values. It's not possible. Let's look at this last guy here, part C. Oh no, sorry, the second to the last guy. Third to the last guy, part C. So part C, I look at him and I say, you know what? I thought this was going to be similar to the last one, but I cannot cancel the square root and the square. I want to, but I can't. It would only be like if it was in the previous example, part B here. Notice it's the entire thing inside the root, t minus 4, the entire thing is being squared. But in part C, it's only a part of it. Only x is being squared, the rest is not. So that's the one thing to keep in mind. I can only cancel a square and a square root if the entire thing inside the root is being squared. But it's not. It's only a part of it. But I think there's a way to make this problem look more like the previous one, part B there. I think I can actually factor what's inside, and I hope it looks like what we have in the previous one. Right now we have x squared plus 8x plus 16. Maybe if I factor that guy, let's see. That's a trinomial with leading coefficient 1, so it'll be the easy factoring method. Let's see, oops, sorry. I'd be looking for what numbers multiply to 16, but add up to 8. That would be 4 and 4, right? And look at that, lo and behold, those are the same factors, so I'm able to write that as x plus 4 parentheses squared, right? If you have two of the same factor, now those freaking square root and square can cancel. Yay! Yay, you guys! Okay. But of course, when they cancel, you're left with absolute values. And right now, I think if I didn't really understand variables, I'd say, wait a second, doesn't that mean the absolute values can go away because there's a plus in the middle? Yeah, there's a plus, but x could be negative. You never know. What if x is like negative 7 or something large like that? If x was negative 7, it would be negative 7 plus 4, which is a negative still. So it kind of depends how large of a negative number x is or how small of a positive number x is. I don't know if this is going to be a positive number altogether, x plus 4, or a negative number, so don't even try to touch it and simplify it. If you have a variable, it's just going to stay inside absolute values. Don't worry about it. Numbers can get rid of, can escape absolute values, but variables cannot. Alright, let's try part D. Okay, looking at this guy, now I've kind of gotten the hang of it. I want it to look like, I want to see if I can cancel a square root and a square. But this isn't a square, it's an 8th power. That power is too large. So what I want to do, if I have to, is I want to make this look like a square root of something squared. So I want to make that power be a square. And I think I'm able to. I can just kind of break that down. The square root of p to the 8th. Is p to the 8th something squared? I think so, right? It's p to the 4th squared. So I can multiply those powers. 4 times 2 would give me 8. And I designed it that way so I can cancel. Now the root and the square cancel. So I remember that the square root can only cancel with a square. So even though I was given an 8th power, I kind of manipulated it until it looked like a 2nd power. Alright, now that the square root and the square cancel, I'm left with what was inside the root, p to the 4th, and absolute values. Now this is the tricky thing now. Wait, oops, sorry. If you think about it, okay, p has an even power. This is an even, or exponent. Even exponents. One thing I can say is they always create positive numbers, right? If you raise anything, a positive or a negative, to an even power, you're always going to get a positive. So for example, what if I raise negative 3 to the 4th power? Negative 3 times negative 3 times negative 3 times negative 3. It's because the negatives kind of cancel each other off. Here's 2 of them, they cancel each other, and here's another 2. So I guess it's like when you have an even number or an even exponent, the negatives, there's an even number of negatives, so every pair of them cancels the negatives. So you end up with a positive number. So for that reason, actually in this one, we're able to get rid of the absolute values. So it's really just p to the 4th because p to the 4th is always positive. Anything to an even power is always positive. no matter what. Yeah, if p was negative, you raise it to the 4th power, it's now positive. If p was positive, you raise it to the 4th power, it's now positive as well. So really, like the previous problems we saw, parts A, B, C, the answers we had to leave the variables with absolute values. But this one, because there was an even power left over at the end, and the other ones we didn't have a power on the variable, it's just the variable plus something or the variable minus something, we couldn't do anything. But if you have an even power left over, you can rest assured that an even power on anything is a positive number, so therefore we can replace, or we can remove the absolute values. Alright, let's try this last one and then we'll move on to something else. Part E, the square root of y to the 14th. So I want to do something similar to the last one. I want to make that look like something to the 2nd power. So I have to think, what to the 2nd power makes y to the 14th? Or in other words, y to what power squared is the 14th power? Or in other words, what power can you, or what can you multiply by 2 to get 14? It would be 7. Since 7 times 2 is 14. Alright, now finally the square root and the square cancel. And you're left with the absolute value of y to the 7. Okay, this is where I ask myself, is this similar to the last one where I can remove that absolute value? Okay, well the key was, what is it, over here, the key was even exponents always create positive numbers. But notice this is an odd exponent. If you think about it, an odd exponent, what if you raise, for example, just to think about it, a negative number to an odd power like 7. That would be, I'm just going to write it out just to illustrate whether we can remove absolute values or not. There's 4 of them, 5, 6, 7, okay. Like in the last one, what is it? Pairs of them will cancel negative. These 2 times each other make a positive 1. These 2 times each other make a positive. These 2 make a positive. But there's 1 negative left over, which is going to make the entire thing negative. So for that reason, it's a negative to an odd power is a negative, but a positive to an odd power is a positive. Like if I took positive 1 to the 7th power, that's 1. So because I don't know if y is negative or positive, I don't know if y to the 7th is negative or positive, so I cannot remove the absolute value. So that's kind of the lesson here is, if you have a variable with an even exponent, you can get rid of the absolute values. But if a variable, maybe I'll write that down, a variable with an even exponent, we can remove absolute values. But if it's a variable with an odd exponent, we cannot. Very confusing, huh? It's hard to remember. It's like square roots are so simple, but all these little details are very complicated and hard to remember. I mean, square roots are fine as long as there's no variables involved, you know? That's when they get complicated. Alright, so the last page here. Got it just a little bit left. There's not too much left for this. It's just kind of more of the same, kind of elaborating. We're going to talk about now, instead of just square roots, maybe cube roots or 4th roots. So in general, what if you had some kind of root? Maybe not a square root. Just in general, let's say the nth root. It could be the 3rd root, the 4th root, 5th root, 6th root, on and on and on. What does it mean? The nth root of a real number a, when raised, it's a number that when raised to the nth power produces that number. But n is the whole number larger than 1. So basically when you have a root, we're going to write it as, so they're talking about the nth root, let's say, the nth root of a number, and then of course n is going to be a number, it's going to be 2, 3, 4, 5. So for example, the square root of a, that's what we've been dealing with this whole time. Just notice we never used a 2. So if you see, if you just see a root with no little number there, that means a square root. There's a cube root, which you're not going to get rid of, because if you got rid of it, people would think it's a square root. A 4th root, a 5th root, you know, it could be all kinds of things. Usually we don't go past 5th roots, it's too complicated. But let's see, we're going to kind of, elaborate on the square root and think about all kinds of roots. And just so we know, the number in here, this little number n, is called the index of the root. We'll be using that word a lot, it's good to kind of keep in mind. Yeah, okay. So the nth root of a real number, a, it's any number when raised to the nth power, which produces a. Okay, it's confusing, but I think when we see an example, or a few examples, it'll make a lot more sense. Okay, let's try to simplify these guys. Let's look at part A. This is asking what's the third root of 8 or the cube root of 8. In other words, this is asking, instead of like a square root, like if it was a square root of 8, that's saying what can you square and get 8, or what can you raise to the second power and get 8. The little 3 tells you now I don't want to raise something to the second power and get 8, I want to raise something to the third power and get 8. That's really what you're asking. What can we raise to the third power to get at number 8? Well, if you're not really familiar with powers of 3, you can just start guessing. Like how about 1 times 1 times 1? Is that 8? No. Okay, how about 2 times 2 times 2? Actually, it is, huh? 2 times 2 times 2 is 8. That means that the cube root of 8 is 2. Okay, so the answer is 2, and that's because if you raise 2 to the third power, you get 8. So that answers that one. And all that writing is just to say the answer is 2. I don't know. I just write all that just in case later on you're looking back at your notes and you say, what the heck? How did I know the answer is 2? What the heck? Alright, let's try the part B. This is where, okay, I'm getting kind of a red flag in my mind. I see a negative inside of a root, but it's actually not bad unless it's a square root, maybe. Because this is asking, what can be cubed or raised to the third power? I'm going to say cubed because it's shorter. To give negative 8. I think actually negative 2 works. So the cube root of negative 8 is negative 2, and that's because if you raise negative 2 to the third power, you get negative 8, right? Negative 2 times negative 2 is positive 4, times 1 more negative 2 makes negative 8. So it's interesting. Square roots, you got to worry about negatives inside them, but a cube root, you don't have to worry about it. There's always an answer. So in a cube root, you can put a negative or a positive inside, and it's going to work. There's always an answer to a cube root, no matter what. Alright, let's see part C here. We've got the cube root of 1,000. So I don't know if we need to write out all those words now that we're used to it. Now you can just say, question mark, what to the third power is 1,000? And if you're not familiar, just start guessing. Like I said, what's 2 times 2 times 2? What's 3 times 3 times 3? But I think because this is a number followed by a bunch of zeros, I think it's 10, right? The cube root of 1,000 is 10. I think that's it, and that's because if you raise 10 to the third power, you get 1,000. Alright, there he is. 10. Yeah, so it's really easy to check your answer on these. Whatever you think the root is, or the answer, all you have to do is raise it to that power, whatever the index is. So this guy, like a 3. Raise your answer to that power and make sure you get the original number. As long as that's true, then you got the right answer. Alright, so part D is saying, what can you raise to the third power and get 27? So in other words, question mark to the third power is 27. But if you kind of ever raise something to the third power, you probably know that it's 3. Because 3 times itself 3 times is 27. 3 times 3 is 9, times 1 more 3 is 27. So there he is, must be 3. And on an exam or a quiz or something, don't feel like you should write all this out. You can just write the answer, 3. There's not really a lot of work to show here. Really the work's going on in your head, and I wouldn't punish you for not writing out the work. So if you just write the answer, that's fine. Don't worry about it. Alright, let's try part E. This one looks a lot more complicated because there's a number and a variable. We've seen this before. If you have a root with 2 things multiplying inside, remember you can split up the root. I'm going to think of it as the cube root of 64, and then give the z his own root as well. There we go. Okay, the 64, now that's saying, what can you raise to the third power to get 64? Well, if you ever get stuck, like I said, this is what I'll do. I'll just start guessing. What's 1 times 1 times 1? 1. Okay, that's not right. 2 times 2 times 2 is 8. Okay, I want 64. Not yet. 3 times 3 times 3 is 27. Okay, that's still too small. What about 4 times 4 times 4? I think that's actually 64. So that's the one we want. It's 4. There we go. And then if that didn't work, I'd keep going. 5 times 5 times 5, and, etc., etc. You'll find the right one eventually. And then the variable thing, okay, this is where I'm thinking, this is saying what can be raised to the third power and give me z to the third power. Or what you can think, though, is that since the index and the power match, they cancel. Like we've seen before. Index and power match, so they cancel. But in this instance, because it's a cube root, I actually don't need an absolute value. Like if it's a square root, you know, if you have a square root with a square inside, you can cancel the square root and the square, but you're going to have to leave absolute value. Anytime you have an odd root, which we'll talk about more coming up, anytime you have an odd root, you don't need an absolute value. It's only when you have an even root. Like if this was an even number here, a second root, a fourth root, a sixth root, but odd numbers like 3, 5, 7, 9, etc., you don't need an absolute value. So that's, we'll kind of write that out more explicitly soon. But it's good to keep in mind, no absolute value necessary if the index is odd. It's only an even index, like a square root, that's an invisible index of 2. But an odd index like 3 here, we don't have to have an absolute value, thank God. Alright, let's try the next one. What do we got? Part F. Alright, we've done a bunch of cube roots, now we're talking about fourth roots. But remember, it's all the same idea. You're just thinking, alright, 4, that's the number of times I would have to multiply something by itself to get 84. So this is asking, what to the fourth power is 84? Or sorry, 81. Why did I say 84? 81. You can just start guessing. Like I said, I'm going to say, well, is 1 to the fourth 81? 1 times 1 times 1 times 1? No. How about 2 to the fourth? 2 times 2 times 2 times 2 is 16. No. What about 3 to the fourth? 3 times 3 times 3 times 3, that is actually 81. That must be it. It must be 3. That's the answer to that guy. And that's because, if you want to write it out, yeah, 3 to the fourth is 81. But really, all you need to write out for this problem is 3. If you just say the answer is 3, I'm not going to say, oh, you didn't show your work. Nah. Don't worry. I figure all that work's going on in your head. Alright. How about this guy? A negative inside a fourth root. So we saw, if you have a negative inside of a square root, it's bad and it's imaginary. But we saw a negative inside of a cube root above in part B, and it was fine. Well, let's see about this guy. You think, I mean, this kind of looks like part A, or part F, right? The fourth root of 81, we have a negative, so I would probably guess maybe that it's like negative 3? Like maybe the same answer, but negative 3? So I'm going to say question mark. Let's see if that's true. If I raise that guy to check to the fourth power, do I get what was inside, negative 81? I don't think so, right? Negative 3 times itself 4 times. Like we've said before, the negatives are going to pair up. Negative times a negative is a positive. Negative times a negative is a positive. It's going to give you a positive 81, but I need a negative. So I think we've kind of learned that this guy's imaginary as well. There's no way you can raise something to a fourth power and get a negative number. I think what we need to kind of spell out here is that, let's see, a negative inside of an even root is imaginary. And by even root, I mean the index is even, you know. Square root is even, or that's index 2, which is even. A fourth root, which is what we're dealing with now, that's an even root. But the one we saw before, the cube root of negative 8, that was fine. It's just when you have an even index, that's the problem. That's when you'll see imaginary numbers. But an odd index, you'll never see an imaginary number. It's only an even index. Alright, let's look at part H now. Ooh, this one looks complicated. But we can always make it simpler by saying, you know what? Inside the root, I see two things multiplying. It's 625 times x plus 3 in parentheses to the fourth. I'm going to give each of them their own root. So you're free to split a root up as long as things are being multiplied inside the root. And then I can kind of simplify each one from there. The fourth root of 625, okay, oh my gosh. That's hard to remember. Well, let me look at, I kind of did some work over here on the very left side. So I'm looking for what can you raise to the fourth power to get 625. I'm kind of on a roll here. I tried 1, I got 1. That's not true. It's 2 to the fourth power is 16. 3 to the fourth power is 81. I need something bigger. What about 4 to the fourth power? That's going to be, that will be 256. Oh my gosh. That's a big number, but still not big enough because what we want to see is 625. Let me try 5. Actually, I think 5 to the fourth power is 625. 5 times 5 is 25. Times a third 5 gives you 125. 125 times one more 5 is 625. So, okay, the answer must be 5 to that one. Oh. So anyway, if you get stuck and you say, oh my gosh, I have no idea what the fourth root of 625 is, or whatever, Just start trying to raise things to this power. 1 to that power, 2 to that power. Keep going and you'll get there eventually. So the root on the left just becomes a 5. The root on the right, I want to cancel the 4th root and the fourth power. As long as the indexes match, the index and the power match, they cancel. That's a good, yeah, I think we've kind of seen that, but it's worth maybe pointing out. If index and power match, they cancel. But there are some times where you have to worry about there maybe being an absolute value, or not. And this one, since it's an even power, or an even index, I do have to write an absolute value. Like with the square root, a square root and a square cancel, but they leave an absolute value. And that's because with square roots, you're worried about imaginary numbers. I don't want to see a negative inside my root, so I'm going to make sure everything's positive by putting an absolute value. We didn't have to worry about that with a cube root because cube roots of negatives are fine. But we've seen that a negative inside any even root, like this, is imaginary. So anytime you have an even root, an even index, like we have a 4, I have to worry about absolute values because I don't want to see a negative inside the root because I don't want to see imaginary numbers. Okay, so how about part I now? Now we're talking about, where are we? The 5th root of 32, all right. I'm not really familiar with 5th roots, so I have to kind of reverse engineer it. This is saying, what to the 5th power is 32? So like I said, I go off to the side and try stuff. What's 1 to the 5th power? 1 times 1 times 1, that's 1. 2 to the 5th power, 2 times 2 times 2 times 2 times 2, that's actually 32. So there it is, right away, it's 2. That's because 2 to the 5th power is 32. The next one, okay, it's almost the same thing. It's the 5th root of a negative 32. So I'd guess it's maybe negative 2 because the last one was 2. And that is true. Because negative 2, if you raise that to the power of the index, 5, you do get negative 32. So that's, like we said, keep in mind, if you have an even index, yeah, we've already said this, but it's worth mentioning again. If it's an even index, like 2, 4, 6, 8, no negatives inside the root. If it is, it's imaginary. But if it's an odd index, like we have a fifth root, or if it was a 3rd root or 7th root, God forbid, the negatives are fine inside the root. Yeah. So good to keep in mind, because I don't want, it's easy to get in the habit of just freaking out when you see a negative inside a root and just saying, oh, it's imaginary. But it depends. Is it an even root, a square root, a 4th root, a 6th root? Then you're right. But if it's an odd root, 5th root, 3rd root, 7th root, oops. Yeah, if it's an odd root, then you're fine, and you don't have to put you don't have to worry about imaginary. Okay, so this next note here just kind of points out something that we've kind of already talked about, but it's making it official. So, okay, if you have the nth root of a to the n, so it's keeping it really general. Like if you have a, I don't know, let me write it down, an example. Like what if you have a cube root of something cubed, like an odd one, or maybe if it was, I don't know, the 6th root of something that is 6. It's just saying if you have an index, I don't care what it is, some kind of index that matches the power, you'll need an absolute value if the index is even. So like this guy, I'll need an absolute value because 6 is an even number. But if n is an odd number, you don't need an absolute value, so this would just be a. So it really depends. You'll say, okay, first thing in my mind I say, well, as long as the index and the power match, like here, oops, shoot, sorry. A cube root and a cube cancel. But when they cancel, you're left with an absolute value only if the index was even, but it's not. It's a third root, so that's an odd power. But here the index and the power cancel since they're the same, but you do need an absolute value since the index was even. But keep in mind you can only cancel if the index and the power are exactly the same. It's not like you have any kind of power or any kind of index they cancel. No, it has to be, notice it's a 6 and a 6, a 3 and a 3. They have to be the exact same number. If they're not, you have to manipulate it until they are. And we'll see that here in example 5. So notice in part A, I have a 4th root of z to the 12th. So that power and that index will not cancel yet. The only way they're going to cancel is if I see the index and the power being the same. Like say if it was a fourth root of something to the fourth power. But I am able to do that, because what do I just say, z to what power raised to the fourth power is z to the 12th. Or in other words, what can you multiply by 4 and get 12? It'd be 3. Alright, now the square root and the fourth root and the fourth power cancel. And you're left with z to the third. And now I gotta ask myself, do I need absolute values or not? I do need absolute values because the index was even. It was an index of 4, which is even. So I need absolute values. And I can't remove them. Yeah, I can't remove them because z could be positive or negative. And if you raise a positive to the third power, it is positive. But if you raise a negative to the third power, it's negative. So this thing could be positive or negative. I have no idea. So I can't really remove absolute values. I don't know what to do with it. I'll just leave it as is. And then part B, I think, is sort of similar. It's the same idea. If I want to cancel that root, I'm going to have to rewrite this guy as, let's keep the index the same. I'm going to need the power to match the index. So I need to write this thing as something to the 9th. And all I have to do is think, well, what power times 9 is 45? That would be 5, right? And now the index and the power can cancel. And I'm left with y to the 5th. But do I need absolute value? No. And that's because the index was odd, sorry. Index was 9, which is odd. So no absolute value necessary. There we go. Okay. So our answer here was absolute value of z to the 3rd. Here was just y to the 5th because I had an odd index. When I do these problems, I always pray for an odd index because then I don't have to worry about the dang absolute values. Man. Right, but notice part C here, it's an even number. 6 is even. So I'll probably have to have absolute values in my answer. Probably. Let's see. Oh! So I'm going to say, and this is the product of two things inside, 64 times b to the blah blah blah. I think what I'll do is give each of them their own root, which will make it a lot nicer. So the 6th root, we haven't seen a root that big yet. I think when the roots get really large like that, the index is 6, or it's 5, or it's 7, 8, 9, God forbid. I have to reverse engineer it, because this is asking what to the 6th power is 64. I have to go off to the side and reverse engineer it. What kind of stuff to the 6th power do I get? 1 to the 6 is 1? That's not right. What about 2 to the 6? Let me see. 2 times 2 times 2 times 2 times 2 times 2. These make 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Ooh, and 32 times 2 is 64. Yay, that's the one. Oh, sorry, yeah, so this is 2. Ah. I was about to write 64, sorry. No, because it's asking, what can you raise to the 6th power and get 64? And we just did 2. 2 to the 6th power is 64. That takes care of that, but this other guy, 6th root of b to the 24th, I'm going to need to write that as a 6th power, because that's the only way the index and the power will be the same. I need a 6 here and a 6 here. So b to the 4th would be what I need in there, right? Because 4 times 6 would make the power of 24. Alright, now that I've written it like that, the 6th root and the 6th power cancel. But remember that the index was odd, right? Or sorry, even. 6 is an even number, so this I need an absolute value of b to the 4th. But just to make it maximally confusing, in this particular problem, I can remove the absolute values at this point because b to the 4th, that has an even exponent. And we kind of pointed this out, I think, a while back in this section. Anything to an even power is positive. And it's kind of because it pairs up a bunch of negatives and makes them cancel each other, since there are an even number of them. So for that reason, we really actually don't need an absolute value here. I mean, I wrote it at first because I said, oh wait, the index was even, so I need the absolute values. But this 4th power kind of counteracted that and said, oh, I know you think you need this absolute value, but don't worry, I'm here to make it so you don't need it. And notice in the first example we did here, part A, it was an even index, which is why I needed an absolute value, but you notice that I was left with an odd power, 3. If that was an even power, like a 4, 6, 8, something like that, I would be able to remove those absolute values. But because 3 is an odd number, I don't know if something to an odd number is positive or negative. It could be either. There's no way to tell. That's why I had to leave it. So very tricky. Oh, almost done with this section. So we're going to kind of bring it back to functions again. So example 6, it says, oh wait. sorry, we gotta look at how to do these. It says, note, to determine the domain of a radical function, like we have here. Oops, that was too zoomed out. Okay. To determine the domain of a radical function with an even index, set the inside of the root greater than or equal to 0 and solve. However, if the index is even, dang it, I was supposed to say odd, sorry. I don't know if, I think yours should be fixed, but mine says even there, it should say odd. If the index is odd, the domain is all real numbers. So if you remember domain, we're going to go back to the function stuff. Domain is talking about what x values am I allowed to put in here? Like what are the okay x values to substitute in here? But then I guess here what you're worried about, I guess for example the first part here, part A, you have a fourth root. So I'm worried about, I don't want to see any negatives in this root, kind of, that's the idea. I need x plus 7 to be positive. Because if it's not positive, if it's negative, then it's going to be an imaginary number, and I don't want to see that. So that's why, like it says, if you have an even index, like this, 4 is an even index. To determine the domain, like it says in the directions, you take what's inside the root, x plus 7, and you set it greater than or equal to 0. That's the directions. And that's all because this is you writing in math what these words say here. I need the inside of the root to be positive. In other words, I need it to be greater than or equal to 0. Because if it's not greater than or equal to 0, it's negative. And now I'll solve for x. This will tell me exactly how to make that happen. If I move the 7 over by subtracting it, what will that give me there? X greater than or equal to negative 7. Aha! So there's your domain. I can only place x values in that function that are greater than or equal to 7. If I put a number that's not greater than or equal to 7 in there, it's going to produce an imaginary number, which is no good. So it's really what you're trying to do when they say determine the domain of the radical function. You're just saying, okay, what kind of values can I put in here and not get imaginary numbers? That's really it. Yeah, that's kind of maybe helpful to say. What values can be placed into the function, the original function we got, without producing an imaginary number. Yeah, so we found them. As long as you put an x greater than or equal to negative 7, you're good to go. But if you try to put something that's not greater than or equal to negative 7, like negative 10 or something, you're going to get imaginary. And I warned you not to put that in there. That's why I put this domain, you know? It's kind of what you're saying to someone. Alright, now part B, it has g of x equal to the cube root of 4x minus 1. And maybe I'll read this again just to see what to do. It says, if the... Okay, first it says to determine the domain of a radical function with even index. But we don't have that. This is an odd index. So what follows that sentence is not going to help me. I need to move on and see what else they say. If the index is odd, okay, like we have an odd index, the domain is all real numbers. There it is. So if you have an odd index, you don't need to do any work. The domain's just, like I said, all real numbers, or you can write it as negative infinity to infinity. That's the same way of saying all real numbers. And the reason that is because if you have an odd root, like we said, you're never going to get an imaginary number. You can take an odd root of a positive, you can take an odd root of a negative. Doesn't matter what it is, there's always a root. So there's no need to restrict the domain. There's no need for me to say, oh, only put x values greater than this, or only put x values less than this. It doesn't really matter what you put in there. It's going to be a positive and non-imaginary no matter what. That's why any radical function with an odd index has domain all real numbers right away, no problem. Let's try part C, and then I think we'll be good. I know this section's kind of overwhelming. There's a lot going on. All right, part C. Now I have to determine, because now that we've read the directions, it says if you have an even index, you have to do this work to figure out the domain. But if, like in part B, you have an odd index, you don't have to do any work. It's just all real numbers. So all I have to decide is if the index is even or odd. Well, this guy has an invisible index, but remember, if you don't see an index there, it's an index of 2, because it's a square root. Now, if we were really dealing with square roots with an index 2 the entire time in the very beginning of this section, we just didn't know there was an invisible 2 there. But the index is 2, that's an even number. So this will be like part A, where we actually do have to worry about the domain. So like the directions say, it says, if you have an even index, to find the domain, you're going to grab what's inside the root, 2 minus 5x, set it greater than or equal to 0, and then solve for x. And that'll tell you the domain. So I'll solve this for x by, I guess I'll move the 2 over, subtract it. That way negative 5x greater than or equal to negative 2. And then I'll divide both sides by negative 5, and then I think I'll have it. But don't forget, when you have an inequality like this and you divide both sides or multiply both sides by a negative number, you have to flip the inequality backwards. Don't forget that. I haven't seen that in a while, but we multiplied or divided, either one, by a negative number. So we have to flip the inequality. So it used to be a greater than or equal to, now it's a less than or equal to. So there it is, our domain is all the x values that are less than or equal to 2/5. So apparently, as long as you put an x value that's less than or equal to 2/5 into that function, you're not going to get an imaginary number. But if you put something larger than 2/5 in, you're going to get an imaginary number, and that's no good. Whew! This is a long section, I know. It's just kind of setting the building blocks, or setting the course for the rest of the chapter. I think the rest of the chapter goes better. It's kind of a long chapter, but I don't know. It's a lot more smooth sailing now that we have all this down, and it'll get easier, I promise. So thanks for listening, and have a nice day.